So before we get too much further into electricity, that kind of stuff, we have to review the main types of circuits. And this should definitely, hopefully, be familiar from grade 9. We're in science to do a bunch of the stuff. Some of you guys took electronics. And hopefully the simulation also looks familiar because we used it in grade 9 quite a bit. But we're going to look at the main types of circuits and how it actually connects to something called Kirchhoff's rules. And Kirchhoff, about 150 years ago, he sort of laid out the rules and the guidelines for how electricity works in circuits, and actually based on a couple of conservation laws. So we're going to look a little bit at Kirchhoff's laws or rules for circuits, and they're sort of conservation laws. And to highlight each one, you look at the two main types of circuits and extract the properties of the circuits. So the first one is based on the conservation of energy, which of course is really important. And basically what it means is as you go around a circuit, you have to lose all of your energy. So the power supply, the battery, gives the charges energy, and as they go around, you have to lose all that energy. So you can't have energy left over when you make it back to the power supply. So you basically get the energy from the battery, the cell, whatever you want, and you have to lose it all. Okay, so you gain it all, and then you have to lose it all before you actually get back. Okay, now we're going to sort of customize this a little bit, but basically the thing is, when you guys do energy, when you guys did energy way back when with electric fields, energy was equal to Q times V. Now, all of the charges in electricity are the same. They're all electrons. So this Q actually cancels out. So the amount of energy is directly proportional to the potential difference or voltage. So you can actually use them interchangeably. So not only can you say you get energy from the cell and lose all of it, you can also reword it and say you get voltage from the cell and you have to lose all of that voltage when you go around. And that's how we typically measure it. So what that means is if we sort of draw a circuit here, I'm going to go black one, there you go. So if I draw a circuit, something like this, just a basic circuit, there we go. If I have my power supply up here, and let's say that is 60 volts, I have to lose all my voltage as I go around the circuit. So maybe I lose 30 volts there, and I lose 20 volts there. This one has to be 10 volts. Okay, so as you go around, you have to lose all your voltage before you get back to the power supply because it's directly proportional to energy. Okay, so let's look at a little simulation and get some other stuff going on here. So I just got to close a little switch there. There we go. All right, so we can see the current flowing around. Okay, now I can crack up my little voltmeter here, and if I measure the voltage on my power supply, I've got 20 volt power supply. So if I check the voltage on my resistor over here, that's minus 6.67. It's minus because it's a voltage drop. My light bulb over here is using 3.3, also negative. And this one over here is doing 10. And if we take those three voltages and we add them up, we will get the 20 volts that was given to the circuit in the first place. So all the voltages have to add up. Now, of course, this is ideal. We're not worried about any internal resistance or any of that kind of stuff. This is all nicely ideal type stuff. Okay, and we can even use circuit symbols too, and it's the same type of thing. Okay, all right, so the voltages have to add up. Now, the other thing about it though, in this type of circuit, and if you guys remember from from grade 9, this is called a series circuit, which means it has only one path, so it's a single path circuit, which is great for simple little things. If you watch the current as it goes around, notice the current is the same everywhere, like the same rate of flow, everything. It doesn't make any difference. Okay, so the electrons are all going the same rate no matter what. So that's one of the basic properties of a parallel circuit, not parallel, series circuit. In a series circuit, you have the exact same current everywhere. No matter where you go, the current is going to be the same. Okay. All right. Now what we're going to do is we're going to sort of take some of these ideas and piece a couple things together. Now, if I go back to the voltage idea, if I take my total voltage, my 60 volts that was up here, that has to be equal to all three voltages and all three, 1, 2, 3 resistors put together. And you could do more. Now what I'm going to do is I'm going to replace this with Ohm's law. V is equal to IR. And if I do that, I can replace this with total current, total resistance. I1 R1 plus I2 R2 plus I3 R3. Okay, so I've replaced all my voltages with equivalent Ohm's law calculations. Now the thing is, the currents are all the same, which means all of these currents actually cancel out. And what I'm left with is just the R's. And it shows that the total resistance is just all the resistors added up. And there could be more. It doesn't make any difference. So that's the thing about series circuits. If you add more and more and more resistance, the total resistance will get higher. The more resistances you have, the higher the resistance, the more the total resistance goes up, and the current will go down. You can actually take these resistors here and I can change their value. For example, this guy's right now at 15. If I increase it, you can see the current slowing down, slowing down, slowing down, slowing down as the resistance increases. So the more resistance you have in series, the circuit does not work as well. Okay, so this sort of highlights the basic properties of a parallel circuit, or not parallel, series circuit. We'll get to parallel in a second. Okay, so the basic things about a series circuit. First of all, there's only one pathway. The voltages have to add up to the total thing. Currents are the same everywhere, and you just add up the resistances. And this all just comes from Kirchhoff's law. Number one, that the conservation of energy kicks in, that the voltages have to add up. Okay. Now, we're going to start looking at his second law, and this is where you need the second kind of circuit in order to analyze what's going on there. All right, so for law number 2, we need a different kind of circuit, and some of you recognize that as a parallel circuit. But law number 2 is actually based on the conservation of charge. You can't gain or lose charge. And basically the idea for that one is, when you have a junction, when the wire splits or comes together, whatever you want, whenever wires split or combine or whatever, the total current in has to be equal to the total current out. So basically, if you have some kind of, if you're at a junction of any kind, basically the total current is going to be constant before and after. That's one nice way to look at it. Okay, so first of all, I'm just going to sketch out my little circuit over there. So, I've got a power supply, I've got a resistor over here, and I've got a light bulb over there. So I'm going to do a little something for light bulb. There you go, something like that. And basically what it means is, you turn this on, the current's going to wrap around, and there's my current right there. When it gets to this junction, it's going to split. Some current will go this way. I'll call that current 1. Some current goes down to the light bulb. I'll call that current 2. And basically, if I would add those two currents, they should give me my total current that was over here. And when they recombine over here, that total current should also be the same. Okay, so the idea is the total current is equal to the sum of the currents put together. Okay, so that's conservation of charge, because of course current is made up of charges, right? And if I get the circuit going, you sort of see how it works. There we go. So you can see the charges coming around. They come around this way. Some go this way to the resistor, and some keep on going down to the light bulb. And you can see that they don't split evenly. Okay, the resistor in this case is harder to go through, so more is going to the light bulb. All right. So there's your basic parallel circuit. Okay, and of course, some of you guys remember this. This is a parallel circuit, and this is where you have more than one pathway. So it's about how many paths you have. Okay. All right. Now, if we incorporate some other stuff, there's something interesting about parallel circuits. If I break out my voltmeter and I put it on my power supply again, I get 9 volts. Apparently it's a 9 volt power supply. And then what a lot of people say is, hey, well, that means this guy's got to be 4.5 and this guy's got to be 4.5, 4.5 for each of them. But if we actually check it out, let's see, this is 9 volts and this one is 9 volts, which some people don't get. But this is one of the things about parallel circuits I'm going to explain in just a second. It doesn't matter where you go in a parallel circuit, you will have the exact same voltages in parallel no matter where you go. It doesn't make any difference where you go, you will have the same voltages in every single point. So what I'm going to do is I'm going to use that idea and apply Ohm's law to the currents the same way you applied Ohm's law in the other one. And if I do Ohm's law, current is equal to V over R, and that's going to be equal to V1 over R1 plus V2 over R2 plus, we could keep on going if we wanted to. Now all the voltages are in parallel are the same, which means all of these V's actually cancel out, and we're left with 1 over RT is equal to 1 over R1 plus 1 over R2. We could keep on going. And this is how to calculate total resistance in a parallel circuit, which is actually more complicated. It's actually the inverse of the sum of the inverses of the individual resistors. If I actually just rewrote this, the total resistance is going to be all of those guys, all those inverses added up, and then you got to take it and you have to inverse it. Now that kind of is, it's way more complicated, but the math behind it ends up that the more resistances you actually put in, the total resistance actually goes down because you're adding more pathways. Okay, so if I were to add a third pathway to the system, the total resistance would actually go down. You can actually see that if I crack out an ammeter. I want to disconnect this light bulb right here. There you go. I bring an ammeter here, and right now this circuit has got 0.36 amps going through it. If I attach the light bulb, if I add a resistance to it, the total current actually goes up because I've added another pathway. No matter how bad the extra pathway actually is, the more pathways you add in parallel, the total resistance actually keeps on going down. Okay, so it's kind of weird. So in parallel circuits, the more paths you actually open up, the more current's going to flow, which actually makes it kind of dangerous. You got to be really careful, that type of thing. Okay, now I'm going to explain why the voltages, are the same everywhere. If you go back to Kirchhoff's first rule, it said when you go around, you have to lose all your energy. Well, this is I believe this was a 9 volt. Yeah, that's a 9 volt cell. So these electrons are getting 9 volts of energy. So as they come around, they don't go through both of them. They only go through one. These charges only go through this guy right here. So they have to use all 9 volts in this one. Some charges go only through the light bulb, so they have to use all 9 volts in the light bulb before they go back. They don't go through one and then turn around and go against the flow so they can go through the other one. It doesn't work that way. It's only one. Okay, and that's why the voltages are the same. My favorite analogy for this is shopping. Okay, let's go back to the other circuit over here, this one over here. Okay, so in this circuit, get rid of that voltmeter, basically, this little cell is giving you money. Okay, money in terms of electricity. Let's crank up the voltage here. Let's say he's giving you 120, get 120 volts to spend. But when you go shopping, you have to go through 3 stores. You have to spend some money in this store. You have to spend money in this store. You have to spend money in this store. You are forced to go to 3 stores. So since you're forced to go to 3 different stores, you have to spend all of your money in combination with those stores. You can't just spend it all in the first one because you have to have some left over for the second one as well as the third one. You're going to 3 different places. Where in the other circuit, in this one, you're not going to both stores. You're either going to this store and spending all of your 25, voltage here, 9. There you go, we got 9 volts to spend. You're either spending the 9 volts in the resistor or you're spending the 9 volts in the light bulb. So that's why the voltages are the same, because you're not going to multiple stores. There's multiple stores to choose from, but you're only able to go to one individual store and that's it. Okay, so that's why it doesn't have to split up its energy payment between multiple things. Okay, so that's why the voltages are the same in a parallel circuit and they have to add up in a series circuit because of how much money you have to spend each one. But this is also why the currents are the same here. Some places, some stores are a lot slower than others. More people can go through the light bulb than this one. Some lines are quicker than others. There's lots of analogies you can use for it, but it works pretty well with shopping. Okay, so those are the basic properties which are should be pretty much review from grade 9. So we'll practice these ideas a little bit more.